So for our first presentation today, our first talk, we have Ahmed Abdelfattah. He is product owner at Open Synergy. He will be talking to us about virtualization in automotive industry. So please give him a hand.
First, I would like to thank you for inviting me today. And I would like to thank everyone for coming to listen about this. I would first like to introduce myself. My name is Ahmed Abdelfattah. I have been here in Berlin with my company Open Synergy for around 2.5 years. I have first started as a developer, and now I moved up a bit as a product owner for our hypervisor product for the real-time systems. I have around 7 years or more, a bit of experience in the embedded software, mostly in the automotive domain. Is anyone here has worked before in automotive? Or yeah, 1, 2, 3, few people. So mostly I think web development and back-end cloud. Yeah.
I work in embedded, but didn't work on it.
Okay. Okay, that's interesting. So I wrote also one hobby is I have is that I'm enthusiastic about investing and financial markets. So if anyone shares this interest, maybe we can have some discussions afterwards. Okay. Now let's get back to our main topic. Okay, so the main topic today is not strictly virtualization. I lied to you a bit here. It's more of how you could apply a concept or a solution from a domain to another domain, and I'm using virtualization as a use case or as an idea that was successfully moved or implemented from one domain to another one to solve a problem in another domain. So here is the agenda for today. We have a bit quick definitions and then a quick intro about virtualization in the cloud. I think you will be the experts in this domain, not really me. And then I will jump about and I will discuss a problem in automotive and how virtualization could help maybe in solving this problem. Okay, so some definitions. What is a hypervisor? Do you know how many people here know what is a hypervisor? Okay, I think that's good. I don't need to define each word that I will use later on. So it's a software that runs on hardware to allow. This is really not a strict definition, or just to to introduce a topic to allow you to run multiple operating systems at the same time on the same hardware, and each guest could run on what we call a virtual machine. So virtualization has been there for maybe much longer than you think. The first the first virtualized OS was called VMOS. It was developed for a mainframe system in the 70s. That was called VM370. That provided virtual CPU, virtual storage, and virtual devices. I would say maybe for you this is a pretty standard, but in the automotive world this is quite advanced features. This is an interesting snippet that I found from the user manual for this user manual was actually published in '72, and when I read that it offers this kind of features, now we are in 2019 in automotive and we are trying to introduce a similar set of features that was already there maybe 40 years ago or more. So what is the state now of virtualization in the cloud? I think you would know more than me here. But I think if we two features that I liked a lot. Oh, this is in Microsoft Azure Cloud. There is this autoscale feature that you could actually create an instance of virtual machines on demand. I know that for most of you, this is maybe a basic, or maybe it's already something that you work with every day, but in our domain, this is revolutionary that you can do something like this. And from performance point of view, it has been gradually adding more. This green is adding hardware-assisted virtualization more and more until now in the AWS cloud. Mostly all the devices are visualized using hardware assistance. This means more and more performance. And I took this diagram from a very interesting blog. If anyone is interested in these performance measurements, he can actually relate to it. Okay, now to automotive, this very slow world that every project takes many years and new technologies are adopted slowly. Okay, what is the traditional electric architecture of a car? This is one example. This is a Volvo XC90. It's actually a very modern car. It's not really, it's not an ancient one. But as you can see here, it has many software features. Each software feature is encapsulated in what we call as an ECU. An ECU is electronic control unit, and you have, if you want to add a new, as a car manufacturer, new software feature, you just package it as a package of hardware and software, and you just throw it around somewhere in the car where you could afford to do it. So you have here ECUs for the motor and powertrain, and ECUs for the infotainment system, these nice screens that you see, and for the airbags, and they are just spread around randomly, not really randomly, but according to the location of this car function, and they communicate over a slow bus. The major bus that's used a lot is called the CAN bus. It's a low rate bus, 125 kilobytes, or maybe up to 500 kilobits per second. And this architecture relies on a central gateway. So here, if we look, we can see this green bus is a low CAN bus, and the red one is the quicker one, or the high-speed CAN bus, and there's a central ECU that actually gateways between this world and this world. One advantage about this architecture is that the car manufacturer could rely on many suppliers, and that you have features that are replaceable easily. If one fails, then you don't have many failures. You could just replace it in your car shop without a lot of technical capabilities. What are the limitations of this architecture that's making it problematic now for car manufacturers as the software complexity is growing? First, that the weight of these EE systems, this number of ECUs, in this car you can count up to 40 ECUs, and in some more modern cars you could reach up to 100. So you could have just 80 kilograms of the car weight, just electrics and electronics, and around up to 5 kilometers of wiring. To connect all these complicated electronics, you have a lot of wiring, and it's really a manufacturing hassle for the car manufacturers. There are 4 trends now that put a lot of pressure on this architecture. These trends make the car software more and more complex. We have autonomous driving, and electrification, and mobility, and connectivity. All these technologies that you hear about daily in the news and in technology portals are actually adding more and more complexity, so there is no room to add more ECUs and more functionality. It's getting a lot complicated for the car manufacturers. The car of the future will be software defined. This is a really very nice chart. It shows the increasing number of ECUs per car from 2006 up to now, and you could see that for the last year, a very luxury car could have up to 100 ECUs, or maybe even more, 110. This is also one nice fact, and I tried to verify it myself, that a luxury car could have 100 million lines of code. That's maybe 4 times the car on an F-35 jet, and around 10 times the amount of lines of code in Android. So we see here that the problem is that it's getting more and more complicated, that we need to add more software, and by the traditional method then you need to add more ECUs. You can't find enough rooms, it's getting more heavier, a lot of connections. It's really becoming more and more difficult. So how can we solve this? How the car manufacturers approach this kind of problems? And here you could notice what I'm trying to convey is that you could borrow this way of thinking, or how the internet guys are coming up with this cloud architecture, and you could map this from their domain to yours. So this is one example of a way that we can overcome these challenges, that the architecture is redesigned, and instead of having one ECU or one control unit per one function, you could consolidate some of these features into a fewer powerful controllers, what we call domain controllers. You could have a set of domain controllers having having more complicated functions, and you could then decrease the number of ECUs in a whole. This also leverages from the fact that silicon industry is adding more power to the microcontrollers, so you could actually have hardware that supports this kind of complex software. This is another step. This is not really clear here. So it says architecture. Just for a moment. This is one other example of redesign, what we call as a zonal architecture. It further consolidates the features into less ECUs. As you see now, we are much less than 40 or even 100, and each ECU from those is having more and more features. And you can also, this is a step toward a fully centralized architecture by having one control unit that's really powerful and really has many features. This could bear savings of around 50% or more to wiring length, because this is really rethought and redesigned to overcome this issue of having randomly challenges is facing these modern architectures. The first challenge is this consolidation of many features that you had split into small units. Now you want to consolidate them into one larger unit. Complicates an already complicated development cycle. So a normal development cycle in automotive world, it could take up to 5 years or even more. I don't know for you, but have you worked before in any project that took more than 2 or 3 years? Has anyone here worked in a 5 years project? this is Automotive. It's very slow, and it's for each line of code you have to do a lot of testing and a lot of quality assurance and checking, because it's safety critical. People's lives are on the line. So the development life cycle is not really write the software, test it and ship it, try it out and see what the bugs are. A major concern by OEMs is that you could how to mix a software or to combine features in different control units together in one large unit with and these software features have different safety criticality levels. These levels we call ASIL levels. So some features are really sensitive, like the airbags, for example. If the airbags fail, then this could be dangerous to human life. But features like the car screen or your touch screen, this is not maybe really problematic to have a few bugs or to fail while you are working on. So this is a concern for an OEM, that how can you combine these together on a more powerful controller, but then how to handle that you have a safety critical feature and one that is not really safety critical. Also, security is becoming a major concern. It's becoming more and more problematic, and it's starting to get into scope. The car before was disconnected from the world. You need to go to the garage to do a software update. You don't really have a lot of connectivity, maybe Bluetooth, but now it's becoming a requirement that the car is always connected, that you can download software, you can update the software as it is your own mobile phone. The users of the car now are expecting that your car is resembling a mobile phone, that you could just while it's running and you are driving, and then the software is updated. So security is becoming a concern more and more. So how can we overcome these challenges? How can we go towards a new architecture that maybe saves time and saves money and decreases the number of ECU, decreases this 5 kilometer of wiring, while we also have these concerns? Then the virtualization technologies comes in, and these software suppliers adopt this technology to face such challenges. So here I'll present you one example. One solution is the Cuckoo's Micro SDK. It's a real-time hypervisor, and it's developed by our company Open Synergy. It will be interesting also to have a discussion afterwards on how, if someone has worked really on the hypervisor, how we can see the differences between a hypervisor in the automotive domain and a hypervisor on the cloud, running a Linux instance or containers or whatever. So this virtualization solution is aiming to address these challenges faced by the OEMs or the car manufacturers. The main challenge here is that you can run multiple software features, but you ensure that the safety critical, let's say that this is a safety critical feature, software feature, and this is not a safety one. How can you ensure that there is a complete isolation between temporal and optimized network devices that are aware of virtualization, optimized interrupt controllers, and so on? So any real-time hypervisor should be able to use these hardware assistant features. Okay, I think I talk shorter than the time, which is not really bad, and I hope that anyone has questions now. Oh, only 5. Okay, so it's not really off. Okay, does anyone has any? Please.
Yes, can you sorry. No, keep this with you.
Well, thanks a lot for your presentation. I'm missing a weak point in the automotive business. Well, not only AV, but it's a latency problem.
Yeah.
When you're talking about cloud, where's the cloud? When I'm driving a car, is it a cloud in Australia? Because I cannot read. Well, it's when it comes to AV, the driving or the computer has to react in microseconds.
Yeah.
Or you're running over.
Yeah.
Yeah. And the latency problem has not yet been solved. We are still around 1 and not 0. So how you will find out a solution?
Yeah, I think this is a very good questions, and I think the title maybe could answer it. That this is very different from hypervisor that you have in the cloud. It's called a real-time hypervisor, and it runs on hardware that supports real-time processing. And by real-time, I mean that missing the deadline is a safety critical issue. So one very critical feature of the hypervisor that it enables these guest OSs or guest software features to run in a way so that you cannot miss any deadline. Latency is safety critical, and it's one of the main features that this hypervisor should address. So it's not something that it's not addressed. It's something that's a critical component in the implementation of this kind of software. I hope I answered your question.
Maybe later.
Yeah.